Let us begin Lecture 10 on modular arithmetic. So first of all, here's the definition. If we have an integer n and we have x and y integers as well, n has to be positive, right? Then x is congruent to y mod n if and only if n divides y minus x. In other words, x is congruent to y mod n if and only if there exists some integer j for which x is equal to y plus nj. All right. So x and y have to be related by addition or subtraction of some multiple of n, basically. All right. And when this is the case, we say x is congruent to y mod n. I should mention that congruence modulo n forms an equivalence relation on the integers. All right. So first theorem, if x is congruent to x prime, y is congruent to y prime mod n, then x plus y is congruent to x prime plus y prime, and xy is congruent to x prime y prime mod n. The proof is pretty straightforward. You just put in the definition of what it means for x and x prime, y, and y prime to be congruent. You know, there has to be a j and a k such that this equation and that equation holds, right? Then I just add them and then group the things with n, which then immediately shows me that x prime plus y prime is congruent to x plus y, right? And likewise, when I multiply x prime, y prime, I group all the things with n together, and again I get xy is congruent to x prime, y prime mod n. And there you go, there's the theorem. All right, so come on. So let's make a definition here. Scooch this up a bit. Come on, paper. Paper's misbehaving. So here's the definition. For integer x and positive integer n, we define x bar. Oops, sorry guys, I'll get it eventually. We define x bar to bar brackets x. I use both notations, all right? To be x plus nz, and what that means is it's x plus multiples of n, right, plus or minus. And the residue class of x mod n, or equivalence class of x mod n, is x bar, okay? And the set of all residue classes mod n is denoted by z sub n, or you can also read this as z mod n, right, or z mod nz sometimes people say. And that's just x bar such that x is in z. But a complete list of that would be 0 bar, 1 bar, 2 bar, n minus 1 bar. All right. And we can define addition or subtraction of these equivalence classes, of these residue classes if you like, by addition or subtraction of their representatives, namely x and y. So x bar plus or minus y bar is equal to x plus or minus y, all of it barred. Right, and the product of x bar and y bar is the, xy all bar. It's hard to put into English, but it's easy to look at, right? So for example, z2 has either 0 bar or 1 bar in it. 0 bar is 2z, 1 bar is 1 plus 2z. In other words, 0 bar is the set of even integers, 1 bar is the set of odd integers. And you can meaningfully add and multiply these sets. That's what's called modular arithmetic modulo 2. All right. Z3, you got 0 bar, 1 bar, 2 bar, and that partitions the integers into multiples of 3 plus 1, multiples of 3 plus 2. All right. And the way calculations work in there, for example, 1 bar plus 2 bar is by definition 1 plus 2 bar, which is 3 bar, but 3 bar is equal to 0 bar, according to the definition. And so any multiple of 3 in Z3 gets set to 0. And over here, 2 bar times 2 bar is 2 times 2 bar, which is 4 bar, but I can subtract 3 and get 1 bar. All right, so more on that as we go on here. let's see here. So, one thing I should probably make sure we're on the same page about before we go on is the connection of these congruence classes to division by n, right? So x is equal to y bar. That's an equation of sets, right? If and only if the remainders of x and y, those are integers, right, are equal upon division by n. So the remainder of x and y upon division by n is also called a residue, but I won't talk too much about that, that language. So I try not to use the term residue that much, okay? I'm not even defining it. So anyway, here we go. Suppose x bar is equal to y bar in Zn, all right? Then x is equal to y plus nj for some j and z, right? So the division algorithm, remember, produces quotients q1 and q2 and remainders r1 and r2, such that x is equal to q1n plus r1 and y is equal to q2n plus r2. So we know that, because the x bar is equal to y bar, there has to be this multiple of j multiple of n that when we add to y we get back x, right? But then by the division algorithm we also have this connection between the remainders mod n, right? Divided by n. And so what this gives me, when you solve it, is q1 minus q2 minus j times n is r2 minus r1. But if we take the absolute value of that equation, we get the absolute value of q1 minus q2 minus j times n, remember n is positive so I don't need an absolute value on that, is equal to the difference of the remainders, right? But that has to be less than n because, remember, r1 and r2 are between 0 and n. You can't have two numbers further than n separated when they're taken from the interval from 0 to n, And of course the n is not included there. So that then says that that can't be anything but 0. That has to be 0. And if that's 0, that forces r1 to equal r2, which is what we were claiming. All right. And then, well, that's the forward implication. The reverse implication, if we have division by n gives us a remainder of r in both cases, then when you take y minus x, the remainders cancel and you get q1 minus q2 times n, which is to say that x and which is to say n divides y minus x, or however you want to slice it. This immediately implies that x bar is equal to y bar because you could write y is equal to x plus a multiple of n, right? Okay, so corollary. If n bar divides x, n divides x. Let me put bars where there's no bars. So n divides x if and only if x bar is equal to 0, if and only if x is equal to 0 mod n. All right, and I should say x is congruent to 0 mod n. Excuse me. X bar equals to 0 bar, x congruent to 0 mod n. This is not equals, this is congruence. Okay. So if you want to make a congruence become an equality, you use Zn. Okay, Z mod n. So here's the proof. It's not especially exciting. I got a sticky note that's getting in my way here. All right, there we go. So n divides x is meaning the remainder of x divided by n is 0, right? Which means that x bar is equal to 0 bar since the remainder of 0 divided by n is 0, using the theorem we just proved. Which is true if and only if 0 is congruent to, x is congruent to 0 mod n. All right. So anyway, there you have it. Let me not belabor these basics that much. Let's look at some examples which got a little more substance to them. I got lots of examples to show you. So here's one. Is 3,672 times 254 divisible by 7? All right, so divisible by 7 would mean that when we look at x bar for this x, mod 7, right, working in Z7, we should get 0. Do we? Well, I don't know. 3,672 I can write as 3,500 plus 172, which is, 7 times 500, which is 7 plus 7 times 20 plus 22, which is 7 times 500 plus 7 times 20 plus 7 times 3 plus 1. The point of all this is any multiple of 7 drops to 0 inside a working mod 7. So all that's left here is 1. So 3,672 mod 7 is 1. 254 bar, so that's 21 times 10 plus 44, which is 30 times 7 plus 6 times 7 plus 2. The point is, multiple of 7, those both drop to 0 in Z7, which just leaves us with 2 bar. All right. And so using the definition, this is equal to that times that, which is equal to 1 bar times 2 bar, which is 2 bar, which is not equal to 0. So no, 7 does not divide x. In fact, what we can say is that the remainder of x upon division by 7 is 2. So, all right. Now I've been using some properties of arithmetic. I haven't really formally stated it yet. So let me just, behave and not put the cart before the horse any more than I should. Scooch out a bit here. So here is properties of arithmetic and Zn. We have a sum of congruence classes is equal to the congruence class of the sum. The product of congruence classes is the congruence class of the product. The kth power of a congruence class is the congruence class of the kth power. As I have been using a lot, x bar is equal to x bar plus nj all bar, right? And if I have n bar times x, that's also equal to 0 bar, all right? So here's a proof of 1 by induction you can look at if you want. I'm going to go on to example 4 here. Let's see here. So I'm in fact, you could prove 2 and 3 similar to the way I prove 1 by induction there, but anyway, let's see here, move on to this example. So I said let x bar equal to that in Z13. Okay, let's calculate the congruence class of 3 to the 20th power. So what I do is I break it into 3 to the 2 times 3 to the 18, which is then 3 squared times 3 cubed to the 6th power. 3 cubed is 27, 27 to the 6th power, all right, that's 9. The other one's 9, right? Now, 27 is 26 plus 1, right? But 26 is 2 times 13, so 26 bar is 0. So this 26 plus 1 just breaks down to 1, and 1 to the 6th power is just 1 again. So we get 9 times 1, which is just 9, so there you go. 3 to the 20th power, mod 13, is just 19. It's just 9, listen to me, 19, dummy. 9, okay. So I sometimes I like these brackets as opposed to the bar notation. It's just like easier to write. So I kind of go back. I've been trying to use bar for the most part, but I will slip back into the brackets. I should mention that if you're working with 2 different moduli at once, if you want to, you could also use like 9 equal to 9 with a sub 13 to indicate that the moduli you're working with is 13. You can adorn with n, right, if you want. But, eventually once you get comfortable with these things, what do? You drop the bars and you drop the brackets, but I won't do that in this lecture. All right, I will try to put bars or brackets everywhere they should be. But when you're doing more abstract calculations later on, it is nice to be able to drop the notation. So anyway, enough about that for now. Example 5. Let's see here. So we have 288 times 45. I want to calculate the remainder of x upon division by 7. So we're going to work in Z7. 288 is 280 plus 8, which is 7 times 40 plus 7 plus 1. So that just reduces to 1 bar. Likewise, 45, you got a copy of 6 times 7 there, so that drops out and just leaves you 3. And so what do we have? 288 is 1 bar, 288 bar, 288 bar is 1 bar, 45 bar is 3 bar in Z7, all right? And so when I multiply these two, I multiply the equivalence classes, which have this lovely reduction to 1 bar and 3 bar, which then multiply to give me 3 bar, right? So the remainder of x divided by 7 is 3. So this is this is a very nice computational method. Let's see here. So next up, I want to talk to you a little bit about the problem of finding an inverse, a multiplicative inverse in Zn. All right, additive inverses are fine. We can always find the additive inverse. The additive inverse of x bar is just minus x bar. Okay, so that's not a big deal. But multiplicative is a little bit trickier because, check it out, like in Z6 we have 2 times 3 is 6 bar, right? But 6 bar is 0 bar in Z6. So here you have 2, look at this, neither 2, oh I guess that's right, neither 2 is equal to 0 nor 3 is equal to 0, right? These are both false. So, another way to say that would be 2 is not equal to 0 and 3 is not equal to 3 bar is not equal to 0. And yet, 2 times 3 is equal to 0. So this makes 2 and 3 bar in Z6 what are called zero divisors. All right, and it follows that 2 bar and 3 bar cannot have a multiplicative inverse. If they did, if they did have a multiplicative inverse, it would allow you to get 2 bar equal to 0. Here, let me just scribble that out. I'm going to put that up here, just side comment, right? If 2 bar inverse existed in Z6, right? Then we could take 2 bar, 3 bar equal to 0 bar, and that would tell me that 2 bar inverse times 2 bar 3 bar equal to 2 bar inverse times 0 bar. But the 2 bar inverse and 2, so these guys would give me 1, which would give me 3 bar equals to 0, which is ridiculous. You can't have the equivalence class with representative 3 is not equal to the equivalence class with representative 0. All right, not in Z6 anyway. So this is just a general fact. Zero divisors can't have reciprocals, basically. They can't have a multiplicative inverse, if you will. So what does it mean to have a multiplicative inverse? Just to be clear, x bar in Zn has y bar in Zn for which x bar y bar equal to 1. If that's the case, then we write y bar is equal to x bar inverse, and we say that x bar in Zn for which x bar inverse exists is a unit, and we let un denote the set of all units in Zn. All right. So if x bar in Zn and there exists y bar in Zn for which x bar y bar equals to 0, all right, 0 bar, where both x bar and y bar are not equal to 0 bar, then x bar and y bar are called zero divisors. All right, so in Zn, you have 3 kinds of numbers. You either have 0, you have a zero divisor, or you have a unit. Those are your 3 choices. All right. So for example, in Z6, we have, here's all of Z6. You got 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. That's the whole deal. All right. As we mentioned, 2 and 3 bar are zero divisors, but 4 bar as well is as well, because 3 bar times 4 bar is 12 bar, which is 0. So 2, 3, and 4 have equivalence classes mod 6, which are not units. And in fact, they're zero divisors. The 0 equivalence class is also not a unit, and it's also not a zero divisor by our definition. Now, on the other hand, 1 times 1 bar is 1 bar, and 5 bar times 5 bar is 25 bar, which is also 1 bar, which means that 1 bar inverse is 1 bar, and 5 bar inverse is 5 bar. So in other words, 1 and 5 bar are both units in U6. If you don't mind, for the rest of this lecture and the ones that follow, I'm going to stop pronouncing the bars as I talk through it because it's driving me nuts. So in Z7 we have 0, 1, 2, 3, 4, 5, and 6, all right? And you can verify that the units in 7 are 1, 2, 3, 4, 5, and 6, because 2 times 4 is 8, which is 1 in Z7. 3 times 5 is 15, which is 1 in Z7. 1 times 1 is 1 in Z7, and 6 times 6 is 36, which is also congruent to 1 in mod 7. Now, what these calculations show me is like 2 inverse is 4, 3 inverse is 5, and 6 inverse is 6, working in mod 7. All right. So, interesting. What else can we say here? So far to calculate inverses, I've done what? I've just used basically just guessing, right? Just calculation. There aren't too many possibilities, and so you can just kind of work it out. But here's the sort of more general what to expect. There's a pattern we should pick up on, right? Which is that the units in Zn are just the x bar for which the greatest common divisor of x and n are 1. In other words, it's the x bar such that x is coprime to n. So if that is the case, right, if x bar is in un, then we can calculate the inverse using Bazoo's theorem. In particular, Bazoo's theorem gives us coefficients, it gives us values a and b such that ax plus bn is equal to 1. In this context, then, that tells us that x bar inverse is actually just equal to a bar. All right. So here's the proof. So let's let x bar be in Zn. Then there exists x bar inverse in Zn for which x bar equal to 1 bar. Well, let's suppose that's the case, right? And then I'm going to let y bar equal to x bar inverse. So we have x bar y bar equal to xy bar equal to 1. That means that xy plus nj is equal to 1 for some j and z, right? And remember, if we have an integer linear combination of x and n being 1, that means that x and n are coprime from our earlier work, right? So there you have it. If x bar is a unit, then it must be that x and n are coprime. And furthermore, if you have x and n coprime, then Bazoo's theorem gives you a and b such that this is true. But then if we look at the corresponding equivalence class, then we're allowed to drop the n multiple, and that just gives us ax bar equal to 1 bar, which then gives us a bar x bar equal to 1, which then, by the definition of inverse, gives us that x bar inverse is a bar. So just that. It's relatively simple. The units are just the residue class, the congruence classes, which correspond to coprime numbers to the moduli. N is the modulus, or I should say modulus. We usually use moduli for like plural of modulus. But anyway, so here's one where I would not advise guessing. All right, so 200, right, mod 200. Then if I calculate the inverse of x for x equal to 20 or 23 or 50 if possible, right? So first up, 20 divides 200 and 50 divides 200, which tells us, of course, the GCD of 200 is 20. The greatest common divisor of 50 and 200 is 50, so those are not coprime, and therefore 20 bar and 50 bar are not units, mod 200, all right? In contrast, 23 is coprime to 200, right, by common sense, but if you'd like some less than common sense, let's do the vector Euclidean algorithm, right? Here it is. So 223 AB, which gives me down 23. The remainder is 16 when I subtract 8 copies of 23 off 200. And then I bring the 16 down. I can fit 1 copy of 16 into 23, so I get B minus a minus 8b, which gives me, this. And then bring my 7 down. I can subtract 2 copies of 7 off 16. It leaves me a remainder of 2. So I do that. I clean things up. And then, let's see here, what do I got? So then we finally get down to the last step. Well, I never bother with the last step, which has remainder 0. I mean, who cares? It doesn't. I mean, yeah, we could go to the wait until we get 0 remainder, but I don't care about that. So I'm after the 1, because the 1 is the when I get to 1, that shows me that the GCD of 223 is 1. But since I've done the vector Euclidean algorithm, I also have this nice equation over here, namely minus 16a plus 87b equal to 1. But when I look at that, put back in what a and b are, namely 223, I got minus 16 times 200 plus 87 times 23 equal to 1, right? So since I'm thinking about this mod 200, when I put the bar over all this, the piece with 200 drops out, and I've just got 87 bar times 23 bar equals to 1, which tells me that 23 bar inverse is equal to 87 bar. So when we're calculating the inverse of a number in Zn, so for small n, like this one, right? I don't need to use the fancy schmancy algorithm for this, right? If I'm working in Z7, I just try multiplying stuff until I see what happens, right? I'm like, oh well, 2 times 4 is 1. I mean, 2 times 4 is 8, which is congruent to 1 mod 7. So that tells me that 2 bar inverse is 4 bar, right? Like, I can just do the explicit calculations and just kind of see it, But once you get the modulus being big, like 200, it's nice that we can fall back on the vector Euclidean algorithm to see how to calculate the inverse. It is what it is, all right? And of course we can use my brother's handy dandy website to do it for us if we're feeling sleepy or such. Although, probably not an option on your test. So I would recommend, the vector Euclidean algorithm for the midterm, right? It's definitely a calculation I will test. I would think that's very, very likely. I would feel like I had failed as an instructor if I didn't test on the vector Euclidean algorithm in the midterm in this course, honestly. Anyway, so here's another one. In Z11, we have GCD of x and 11 is 1 for everything except for 0, right? So the units are everything except for 0. And for a small enough n like this, I think we can just find the inverses through ad hoc calculation. So what do I mean by that? Well, here's how it goes. So I'm like, 2 times 2 is 4. Okay, great. 2 times 4 is 8. Okay, good. 3 times 4 is 12. Oh, hey, 12. 12 is 1. 12 is congruent to 1 mod 11. I just found that 3 inverse is 4 and 4 inverse is 3. Hooray. And then I'm like 3 times 7 is 21. All right, I know that. Hey, but 21 minus 22 is minus 1. So like 3 times 7 is equal to minus 1. And so if I square this, then I get 9 times 49 is 1, because minus 1 squared is still 1. And hey, that gives me 9 times 5 is 1, which tells me 9 inverse is 5 and 5 inverse is 9. So if you find a product of things equal to minus 1, you can square it to find inverses. That's kind of a neat trick. And then there's some other things that are kind of like self-inverse, like 10 squared is, well, 10 is minus 1 here, right? And because we're working mod 11, and so 10 squared is 1, which means 10 is its own inverse. And it turns out that 6 times 6 is 3 bar, right? And then I'm like, oh, wait a minute, hey, I know that the inverse of 3 is 4. So if I take this 6 times 6 equals to 3, and I multiply it by 4, 6 times 6 times 4 is equal to 3 times 4. Well, that may give me something interesting, mightn't it? Mightn't it? Is that a word? I don't think that's a word. I don't believe that's actually a word. So my apologies if you're an English teacher. But if you're an English teacher, why are you taking a graduate math class anyway? I mean, if you are, more power to you. But I guess teachers may wear many different hats, huh? Let's see here. So 6 times 6 times 4 works out to 6 times 24, right? But 24 is congruent to 2 mod 11, so we get 6 times 2 is, well, of course, 6 times 2 is 12. Duh. 12 is 1, so 6 inverse is 2, and 2 inverse is 6. So, I mean, I'm not saying you have to do these calculations to do this. I'm just saying these kind of calculations might be helpful to you in larger numbers, you know. I'm just playing around here. So 7 times 7 is 49, which I subtract 44 from it because I get 49 is congruent to 5 mod 11. And then I'm like, oh, I got a 5 here, so if I want to make that turn into a 1, I can multiply by 9, you know, because 9 is the inverse of 5. So I multiply this by 9 bar, and that converts 5 times 9 bar to be 1 bar. On the other hand, I get 7 times 63 bar, which works out to 7 bar times 8 bar, so 7 inverse is 8. And of course, as always, 1 inverse is 1. So I didn't have to use the vector Euclidean algorithm on this one because, you know, you can just kind of bang your way through it. Example 10. Suppose you want to solve 3x congruent to 10 mod 11. So this congruence we can trade for this equals. This is something I want to try to communicate to you. You have a choice. You can either work on a congruence problem or a equality problem in Z11. So I personally prefer the abstract equality to the concrete congruence. But, you know, different strokes for different folks. But anyway, so I get 3 bar x bar equals to 10 bar in Z11. And the thing is, we just figured out that 4 bar was the multiplicative inverse of 3 bar. So if I multiply this equation by 4 bar, all right, that gives me 1 bar x bar equal to 40 bar, but 40 bar is congruent, 40 is congruent to 7 mod 11. 711. So we get x bar is equal to 7 bar, which translating back gives us x is congruent to 7 mod 11. And there's your answer. So it looks like we have a shot at solving congruences when a particular pattern is seen, right? When the number multiplying x is like relatively prime to the modulus. What happens if the modulus here, the modulus is 6, right? And we can't just, and we got 2x is equal to congruent to 4 mod 6, right? So I can't use the trick I just used in example 10 because I don't have a 2 inverse in Z6, right? So I can convert this to 2 bar x bar equals to 4 bar in Z6, right? But I can't, there's no 2 bar inverse, so like, what do I do, right? Well, the neat thing is, you're working in Z6, there are 6 things. 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. So there's a method we can use here that you never used in elementary school because you always had, you know, too many answers possible, right? But here we only got 6 answers possible. So you just plug them in. Plug in 0, plug in 1, plug in 2, plug in 3, plug in 4, plug in 5. And what do you get popping out from 2 times those things? You get a 0 bar, a 2 bar, a 4 bar, a 0 bar, a 2 bar, a 4 bar. So only x equals 2 bar and x equals 4 bar actually it's 5 bar rather, actually solved it. The others did not. So we find 2x congruent to 4 mod 6 if we have x congruent to 2 or x congruent to 5 mod 6. So cool, we could solve it. And this time, instead of having a unique answer, we actually ended up with 2 answers. Interesting. And finally here, parting thoughts for this this lecture here. If in the previous example, basically the same previous example, I had 2x congruent to 3, if I had 2x congruent to 3, or if I was trying to solve 2x congruent to 5, if I was trying to solve 2x congruent to 1 mod 6, I would have found no solutions, because as I look at the values of 2 times x, or rather 2 bar times x bar, I did not get a 3 bar, a 5 bar, or a 1 bar in this list, right? I got my 0 bar, 2 bar, I got 0 bar, 2 bar, 4 bar, 0 bar, 2 bar, 4 bar. So only if I have 2x congruent to 0, to 2, or to 4 do I get solutions. So if I had 1, 3, or 5, no dice. All right. And finally, I just mentioned this theorem. If a bar is a unit, then it's clear from what we've done already that AX congruent to B mod n has a unique solution. X is congruent to CB mod n, where I'm saying this number C is the number whose equivalence class is the inverse of A bar. And the proof is essentially just the calculation we did already. But I should mention page 46 to 52 in Jones & Jones Elementary Number Theory gives nice advice on how to solve any linear congruence, and we'll cover a lot of that in Lecture 12. So thanks, folks. I'll pick it up here next time.